Good evening, everyone. Okay, welcome to our lecture. Okay, for this module. Okay, so let me get started. So I've uploaded some files a while back. All right, don't worry. I will explain later what those files are and what we're going to be using them for. For today's class, we are going to be finishing up the lecture 4. All right, on Mips, and then we're going on to lecture 5, which is on more a deeper understanding on Mips. Okay, and then we will be able to look at tutorial 2. So tutorial 2 questions I just uploaded to Luminous, but we will go through those questions next week. Okay, and I also uploaded some other software material which I will explain later in a while. Okay, so let me get started. All right, by sharing the screen here. Okay, so let me just do a quick recap of where we were last week. So last week we got introduced to the Mips assembly language programming. Okay, every processor out there has its own assembly language syntax. Okay, if you deal with Mips processors, they have one Intel, Motorola, or ARM. Because every processor has their own syntax, and some of this the syntax or the instructions that are available to us may seem a bit uh, in a sense not so convenient, okay, for programming wise. Okay, and you may think, why don't I have an instruction that can just do this for me in an easier way? Why must I go through like around the bush just to do something with assembly language? Okay, so the general idea you must understand is uh, we want, or when engineers design processor cores, they want to maximize the the functionality with minimum resources. Okay, so that is why you may not see all the instructions that you think you should have, but you can still implement what you want, but it's just you may need a few more steps along the way. Okay, so the idea is you want to keep it simple and reusable. Okay, so that is the idea, or the reasoning why you will see that how come I have this instruction but I don't have something else that is a bit similar but can be a bit more useful. Okay, so you have to make do with what we have and implement the logic with the instruction set that is given to us. Okay, so we started off with this. We started getting familiarized with the Mips instruction set architecture with this instruction here, which was the basic R-type instruction where you have two source registers and one destination register. Okay, so let me move on here. So we talked about the relationship between how C and assembly language code may look like. Okay, so the idea that we saw in all these slides was that ultimately C statement can be very complex. Okay, but when we translate that statement into assembly language, or the compiler does it for us, it will have to break it up into a lot of sequential steps. When the compiler does it, it has its own rules on how to interpret the C and do this translation. When we are writing our own code, we have some flexibility in how we want to, what kind of instructions we want to use to implement that same logic. Okay, so the idea that we saw was when we write our code, we have variables, okay, in C, but ultimately those variables will be the data in those variables, which are in memory locations, will eventually be loaded to internal registers. Okay, and then the processing is done using internal registers. Okay, so that is the important thing that you must understand about how the processor works over here. Okay, so these are some of the examples we saw. Then we also saw this extended instruction called the I-type. Okay, so in this I-type instruction, basically what you have is you have the ability to specify an immediate value. Okay, so by specifying an immediate value, you are able to specify one source register over here, one immediate value, and then perform some arithmetic or logical operation, and then you write the destination. You write it to the destination register. In terms of the immediate value, uh, the range of the immediate value is basically limited to what we call the 16-bit 2's complement form. Okay, so we will look into this again a bit later. All right, why we have this 16-bit 2's complement as the limit or the range of the uh, immediate value that we can specify in the instruction. Okay, so we saw about the zero register, logical operations. So all these are things we have gone through last week, so I'll not go through in detail. I'm just doing a quick recap of it. So we also talked about the logical operations, the AND, OR, and so on, as well as shifting operations. And then we were talking about this masking. Okay, so why is this masking important? Okay, or bitwise operations important? Because they allow us to manipulate or focus on specific bits in a register, and then we are able to get some useful information. All right, when we did the number systems, all right, so we saw that, okay, I in number system I have a decimal. Okay, I can convert it to a binary, and when I do that, uh, we see that there are just two different ways of representing a number. So when you look at this binary numbers, okay, or binary strings, you tend to, of course, we tend to think of them as representing a number, okay, which could be the case, all right. But in the context of the processor and the registers, that information may not actually be representing a number, but in fact, the different bits could be representing different sets of information for us. Okay, so in that 32-bit register or 8-bit register, whatever, maybe some of these bits represent some information about the state of the processor, or some other bits represent some information regarding the output of some operation that was carried out, and so on. So uh, in some cases, when we have a register with this information, we don't necessarily look at it as a full register representing some number, but we are interested in some bits or group of bits that represent some information. So one register, if you break it up, can represent a lot of information for us. Okay, so in this example, basically what we are doing is we are looking at bits 13 to 10. Okay, and we are saying that we only want to uh, focus on these 4 bits. So the T1 is the original register. Okay, and we have a lot of this full 32 bits here. But instead of looking at the full 32 bits, we only want to look at bits 13 to 10. So I create a mask. Okay, so this T2 register is a mask where those bits are 1, the rest are 0. And the idea of using the mask is that after I do an AND operation, okay, because when I do an AND with a 0, I do an AND with a 0, I will get a 0. When I do an AND with a 1, I'll get a 1. Okay, so that is the idea. So after that, I will be able to focus on the bits that I am really interested in. Okay, so let's look at this. Okay, so just give me a minute here. Where I think my the mapping of my tab, my writing pad is a bit off. I need to recalibrate that. Just give me a minute, then I'll come back in. Okay, sorry about that, because previously I calibrated it to for my external monitor, so that's why the writing was a bit off just now. Okay, so let me carry on here. So in this example, we are told that we are interested in the last 12 bits of the word in register T1, and we want the result to be stored in T0. Okay, so the last 12 bits means bit 0. Okay, so this bit 0 to 4, sorry, bit 0 to 3, 4 to 7, 8 to 11. So this is these are the last 12 bits that we want. So since we want to keep these 12 bits, the mask should be designed such that the 12 bits here are ones, the rest are zeros. So when I do a AND operation, what I will get in the result is it will have only the last 12 bits, which are from the original T1 register, and all the other bits are cleared to 0. Okay, so this is how you can do it. So in here we also told you that the AND has also an immediate version called AND-I. Okay, as we saw in the earlier slides, the I is for immediate type instruction. That means you can specify sort of constant value in the instruction. Okay, so for setting a bit in a register, we will OR it with a 1. Okay, because when you look at the OR operation, okay, the OR operation is such that 0, okay, doing a OR with a 1 will give me a 1. 1 OR with a 1 will still give me a 1. Okay, so as long as I do a OR with a 1, the output will be a 1. Okay, so if I want to force certain bits to 1 in my output, all right, I can just do a OR with a 1. So in this case, T1, I'm doing an OR operation with this immediate value where the lower 12 bits are 1. So that will force the lower 12 bits to be automatically set to 1. Okay, so this is again, these kind of techniques are important in programming because in some cases you want to manipulate only certain bits. So you want to clear certain bits or you want to set certain bits. So you need to make sure that the AND or OR operations are used, okay, to make sure that the other bits are not uh, changed because of these instructions. Okay, uh, so again, these are some of the quirks of the processor that you see. You don't have a NOT instruction. So the NOT is to do an inverse. All right. So when you want to invert, that means 1 to 0, okay, 1 to 0 and 0 to 1, you say you do a NOT, okay. But there is no NOT operation, okay, inside the processor. But what you have is a NOR instruction. So how do we get a NOT operation? We are able to get a NOT operation done by doing a NOR with a 0. Okay, why? If I do a logical 1, do a NOR with a 0, okay, I will get a 1. Okay, and I have a 0, do a NOR with a 0, I will get a sorry, this one will become a 0, here will become a 1. Okay, so the way to look at it is you just imagine it's an OR. So 1 OR with 0 is a 1. So if I do an invert, it will become a 0. 0 OR with 0 is a 0. So the inverse of this is a 1. So if you look at this part here and you look at this part here, what you are seeing is it has flipped. Okay, the 1 has become a 0, 0 has become a 1. Okay, so by doing a NOR with a 0, it is equivalent to performing a NOT operation. Okay, and for this question here, why is there no NOT instruction? Again, it comes back to what I mentioned earlier. As far as much as possible, we want to maximize the use with minimum hardware. Okay, so since I can perform this operation, this NOT operation or flip invert operation with a NOR with a 0, so it doesn't it's not necessary for me to have another instruction just for this. I mean, right now you may think, why don't I just add an instruction, all right, and just solve this instead of complicating things. Okay, so later on when we are going more in depth into the Mips hardware architecture and looking at the control logic, the data path flow, and so on, then you will start to see why keeping things simple actually makes a big difference. Okay, and adding an addition or sort of extending one more instruction can is not as easy as we think. Okay, you may need to provide a lot more changes to the hardware to support a new instruction. So these are things we will actually get to see later on when we're looking at the hardware in more detail. Okay, so there is also a XOR operation. Okay, and we can also perform a NOT operation with exclusive OR. Okay, because exclusive OR with a 1. Okay, so if I say 1, I do exclusive OR with a 0. Okay, the answer will become sorry, 0 exclusive OR with a 1, the answer will become a 1, and a 1 exclusive OR with a 1 will become a 0. So again, if you look at this and this, you see that it has flipped. Okay, so the idea is when I do exclusive OR with a 1, it is again a NOT operation. That means I'm flipping all the bits. Okay, so again, you have some instructions with R type, some only with I type, again to make sure that we keep things simple as possible, because you may be able to achieve some functionality with other instructions. Okay, so we don't need to implement all instructions. Okay, so this is an interesting thing. How do I load a 32-bit constant into a register? Okay, okay, so how do I do this in the first place? Okay, so if I look back here, okay, uh, if I go back to the slide on the mask, okay, so for example, this, okay, let me go back to the earlier instruction here. Okay, so this instruction, for example, okay, so in this instruction, you can see that T1 has some data, and I'm going to do an AND operation with a mask. So this T2 has to be loaded with this 32-bit value. Sorry, 000 and 111100. Okay, so I need to load T2 with this 32-bit value. Okay, and how do I do that? Okay, why is that an important thing to look at? Because we must understand that all our registers are 32-bit. Yes, so all our registers are 32-bit, which means that all my instructions, okay, just now the add instruction, AND instructions, okay, the OR instructions, all the instructions are also 32-bit. So this means that all instructions are 32-bit. Okay, my registers are 32-bit, my instructions are 32-bit. So how do I put a 32-bit value into a register? Because to put a value into a register, I must have an instruction to do it. Correct? I must have an instruction to do it. So when you say that there's an instruction to do it, some bits of the instruction are what we call the part of the bit, part of the instruction that tells the processor what to do. So I want to load a value to a register. So even though my register is 32-bit, I actually cannot use the full 32 bits for data. Okay, when I'm executing an instruction, because the instruction itself takes up some space. Okay, it is just like it's just like thinking of your hard disk space, for example. Okay, when you buy a laptop, if they tell you is 512 gigabyte of hard disk space, you will never get the full 512 gigabyte hard disk space, because you know that some of it is needed for the OS. Correct. So when you boot up already, some amount of memory is already used up, and what is left is what you can use. So the same thing here. So the instruction is 32-bit, means some bits have to be reserved for the processor to execute the instruction. So you only have a certain number of bits that are left. Okay. So in order to solve this or overcome this current issue, what the Mips processor does, it actually allows us to split up the 32-bit, okay, into two separate or loading of a 32-bit value into two separate instructions. Okay, so what are two separate instructions? The first one is called LUI, load upper immediate. So when you say load upper immediate, what is happening? Okay, so this is my T0 register. Okay, the T0 register is 32 bits. Okay, but I'm going to load only the upper 16 bits first with one instruction. Okay, so that is where the LUI instruction comes in. Okay, so when I do this LUI instruction, what the processor also does for me is it makes sure that the lower 16 bits are all zero. Okay, the lower 16 bits are all zero. Now, the next step would be I'm able to do an OR immediate instruction with the other 16 bits that I want inside the lower portion here. Okay, so this value here, I want this value to be actually here in the lower 16 bits. So I do a OR operation, OR immediate operation. Okay, and as what we know, when I do a OR with a 0, what happens? Basically, the 1 OR with 0, it will become a 1, 0 will become a 0. Okay, so the value that I want will now be occupying the entire T0 register, okay, that I wanted to do in the beginning here. Okay, so in order to load this entire value, it means the entire value I wanted to load into the T0 register is this. Okay, but I cannot load it one shot. So what I need to do, I speed it up. So first the upper 16 bits with the LUI instruction, that will load it in the upper 16 bits and make the lower 16 bit 0. Then I do a OR immediate with the lower 16 bits that I want. Okay. So as a result, the full 32 bit will now be in the register. Okay, so that is how you are able to do this. Okay, so these are again a quick review of some of the instructions that we have gone through or reviewed over here. We will get to experience and practice this more along the way with the tutorial as well as the lab that we will be doing. Okay. Okay, so with that, I will end this particular set of slides. Okay, and let me move on to the next set of slides. Okay. Okay, so you can open up your next set of slides, lecture 5. Okay, so this set of slides is inside your week 4 folder, which I uploaded a few days back. Okay, so in this set of slides, okay, we are going to be going through more Mips instructions to better understand how the processor is actually executing code at the assembly level. Okay, so once we are done with understanding the assembly language instruction part, then we'll be able to look into how the processor hardware uh, deals with these instructions. Okay, so that is where we're going to look into even more at a lower level, at the hardware level. Okay, so we're going to look at memory, load memory instructions, which are the load word, store word. Okay, and some example of how, for example, an array might be stored in memory. Okay, and we're also going to be looking at some code where you have decision making. Okay, so just like how we have if else statements in C. Okay, how do we do that? And at the same time, loops. Okay, how do we write loops in assembly language? Okay, so let's look at memory organization first. So generally what we say is memory can be viewed as a large single dimension array of memory locations. Okay, so it's just one continuous block of memory locations. That is how we can view the memory in a system. And every memory location has a unique address. Okay, so if you think of the entire memory as an array, okay, and the size depends on how big your memory is, then every element you can say you can sort of reference it using the index. Okay, and given a k bit address, you have the size of 2 to the power of k. Okay, so there's two parts to this. One is the address, one is the content. Okay, so the address refers to how big is your address bus. Okay, so the address bus in general would depend on the kind of architecture or the processor you're dealing with. Okay, so for example, okay, if you let's say make it very simple, you just say I have an 8-bit address bus. So if I have an 8-bit address bus, that means I have 2 to the power of 8, which is 2, 5, 6 different addresses. Okay, that means if let's say this was my memory space, I will start from 0, go all the way until 2, 5, 5. Okay, so that is referencing the 256 different address locations I have. Okay, so that is the address part of it. The next part is the actual content. So within each address, how much data do I have? Okay, so it could be 8-bit data, it could be 16-bit data, it could be 32-bit data. So it all depends on the hardware design, the system, okay, and how everything is put together. So there are many sort of variables in this. Okay, so it is not fixed. It depends on how you are designing the architecture of the system. Okay, so in this example over here, what we see is in every address there is 1 byte of data. Okay, 8 bits, 1 byte of data in every address. Okay, so this is basically what we call byte addressing. Okay, why? Because every address location which is unique has a single byte of data. Okay, it is also possible, okay, that in some cases you have word addressable memory. Okay, that means every address you store 1 word, okay, of data. That means 4 bytes if you want to generalize that. Okay, so again, word is usually 2 to the power n bytes. Okay, in many systems you can say it is 4 bytes. In some cases it could be 8 bytes and so on. So it all depends on the size of the processor's internal registers. Okay, in most cases the register size of the processor is an indication of how big your data bus is going to be. Okay, so just now I mentioned address bus, and now I'm talking about data bus. Okay, so let me just give you some overview. So when you talk about your processor, okay, you definitely need memory. Okay, and there are 3 main. Of course, there are a lot of other things besides processor and memory, your peripherals and so on. But between the processor and memory, there are 3 main buses that will go. One is the address bus. Okay, and that is to tell the memory which address I'm referring to. Okay, within the memory space. The next is your data bus. So your data bus can be two-way, okay, depending on what you're doing. And of course, the last part is basically your control lines. Okay, these are basically your control signals to sort of synchronize and do the necessary handshaking. Now, in terms of address bus, just now we saw the size of the address bus depends on how much memory space you have in your system. Okay, the size of the data bus is in many cases tied to the size of the internal registers of the processor. Okay, so take for example, I have in our case Mips, I have a 32-bit processor. That means all my internal registers can store 32-bit of data. So when I want to read from memory, it makes more sense for me to deal with a memory and have a data bus that transfers information 32 bit at a time. Okay, so that is of course the most obvious and efficient way of doing it. You can of course design system to say that I have 32-bit processor, but I use 8-bit memory. Okay, but why is it inefficient? Because that means every time I want to load a register, I need to do 4 load or 4 load instruction. I need to fetch from the memory 4 times, then I can fill up one register. Okay, so it is possible, but it is not efficient. Okay, so that is why we say that in most cases we can take the register size to be an indication of how the data bus is going to be configured, and also how the memory is going to be accessed. Okay, so in this example, okay, and the rest of the slides, we will stick with the convention of using word to represent 4 bytes. Okay, now when a word represents 4 bytes, we want to make sure that they are aligned in memory. So aligned in memory means we always start from address 0. So if I start with address 0, then 0, 1, 2, 3 will be 1 byte, sorry, 1 word. Then starting in address 4, 5, 6, 7 will be the next word. Okay, so you can see the 2 green blocks over here. These are what we call aligned words. That means you are accessing this 4 byte exactly at the boundary, okay, of this 4 byte word. If you try to access a word that is somewhere in between, then what will happen is considered a misaligned word, okay, which should not be done. Though it can still be done, okay, but why we say it should not be done is because since everything is aligned to the word, okay, in this system, we should deal with only word-based access that is aligned to memory. Now, this is an interesting question. How do we quickly check whether a given memory address is word aligned or not? Okay, so to answer this, let's look at the addresses over here. So in this case, is 0 to 7. Okay, if I represent these in my binary form, you see that this is 0, 0. Okay, so let me put it in 4 bits. So 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. Okay, then 8 is the next word. That will be 1, 0, 0, 0. Then 9 will be 1, 0, 0, 1, and so on. Okay. Now, if you look at this sequence, you will see that in order for me to know whether I am having a word aligned address, all I need to do is look at the lower 2 bits. Because if the lower 2 bits are 0, that means it's actually the start of a new word. Okay, so that is how you can very easily know whether you are accessing a word aligned address or not. The last 2 bits must be 0. Okay, so that is an indication that it's a word aligned access. Okay, so now let's look at the Mips. Okay, so as far as the Mips is concerned, it is basically what we call a load store register architecture. Okay, why is it a load store register architecture? Because the processor, okay, the Mips itself cannot directly manipulate information in the memory. Okay, so if this is my memory where I store my instructions and data, I need to fetch this data in. So that is where we call the load. Okay, so load is basically equivalent to saying fetch, okay, from memory. And then I do all my processing, and once everything is done, I write back to memory. So that is where the store comes in. The store is write back to memory. Okay, so I do a load, I perform all my processing, and finally I write back. Okay, and we say that each we have 32 registers, and we have seen before, and everything is 32 bits long, and every word contains 32 bits. Okay, and memory addresses are also 32 bit long in the Mips architecture. So the address bus is also 32 bits, the data bus is also 32 bits. Okay, so that is the information that we can see here. Okay, so now in terms of uh, 32 registers we have seen. Okay, so that part we have covered. Now in terms of memory words, okay, so in terms of memory addresses, we say there is 32 bit. Okay, but what Mips does is Mips actually uses byte addresses. Okay, but it is storing word information. Okay, so let me come back to this and show you what I'm talking about. So as you can see here, in every address, we say it is storing 1 byte of data. So every address only stores 1 byte of data, but the Mips processor deals with 1 word at a time. So when I read from address 0, I will actually be reading all the 4 bytes starting from address 0. Okay, because the access is always word access, but the addressing is going in a byte incremental format, which means that if I read my first word from address 0, okay, this is my first read from address 0, the next word is not starting at address 1, it is starting at address 4. Okay, so the address of words adjacent to each other are actually changing by 4, not by 1. Okay, because by 1 is the next byte. Okay, but we're not doing byte access, we are doing word access. Okay, so that is why consecutive words will differ by 4. Okay, so we will see this a bit more clearly later on. Alright, so now if you're still not sure how this actually affects your programming, we will see in a while. Okay, but just understand that the memory itself is storing information such that every address has 1 byte. Okay, so address 0 has 1 byte. Okay, address 1 is 1 byte. Okay, 2 is 1 byte. And address 3 is 1 byte. So as far as the address is concerned, when the address is incrementing, we are looking at byte by byte. Okay, but since I am always doing word access, the information always is load. I always do a load and store in terms of word. So when I do one word, this is word 0. The next word, word 1, will start after this. So it's always multiples of 4, differ by 4. Okay, between 1 and the next. Okay, so let's look at this example here. So this LW here is basically what we call the load word instruction. Okay, and this is in many cases one of the first few instructions you will do when you're going to write your code, because before you can do any processing, you need the data to be inside the register. Okay, you need to be the data need to be inside the register. So I need to fetch this data from the memory and put it into my register. Okay, so this is basically the two instructions you will use. One is load word and one is store word. Now this instruction, the format is slightly different, okay, from what we saw earlier on, where we had the R type and I type. Okay, so in this memory instructions, this is the register. So the format is, this is your destination, this is your source, and this is your offset. Okay, so these are the three parts of this instruction here. So how does the processor interpret this instruction? So when you say, so let's look at this part here first. So here we have 4 bracket S0. So S0 is the source. That means S0 is treated like a pointer to memory. Yeah, S0 is treated like a pointer to memory. So S0 is containing, okay, what S0 contains is the address of where I want to point to in memory. Okay, so this S0 is pointing to the address, okay, or pointing to the memory. That's pointing to the memory. So S0 contains the address, and this address is actually the memory. So it's pointing to the memory location. Okay, and the offset is basically the offset that is added. Okay, that is added to the source register. So when I put 4, that means I take 8000. In this case, 8000 is the memory location, and I add 4 to it. Okay, so whatever is S0, S0 has a value of 8000, so it's pointing to address 8000. But then I add 4 to it, so the offset is +4. So the final address I'm pointing to is 8004. Okay, so that's the first step. Okay, you must understand that this second half of this instruction has two parts: the source, which is the base address. Okay, think of it as a base address where I'm pointing to, and then I add to an offset. Okay, so that gives me the address that I want to now reference. So this is a load word instruction. So in this instruction, basically what I'm going to be doing is I'm going to be reading the data from this memory location. So this is the LW, load word, right? So word means is 4 bytes, okay, 4 bytes or 32 bits. So I'm going to read this 4 byte data, and then I'm going to transfer it over to my T0. T0 is my destination register. Okay, so the data in my memory location starting from 8004 will now be transferred to my T0 register. Okay, so that is what this load word instruction is doing for us. Okay, how about store word? So store word is the opposite, correct? That means I have some data in my register and I want to move this data in my register to the memory. Okay, so in this case, okay, we say that the source, okay, or the actual data is this. All right, and this is your destination. Okay, and in this case the destination is still a pointer. So S0 is still holding the address of where I want to point to in memory. Okay, so it's holding a value 8000. That means I want to point to memory location which has an address of 8000. Okay, and then I add the offset, so this plus this. Okay, so this will give me the final address of where I'm pointing to. Then I take my data in my source register and transfer it over to the memory. So that is what SW means, store word. Take the data from my processor, from the internal register, and store it into memory that is specified by the base and offset. Okay, so these are the two instructions that basically reference the memory space. Okay, so in terms of how this relates to, in terms of the idea of having one word represented by 4 bytes, okay, of addresses, or with 4 different addresses because of byte addressing. Okay, so this example is a good way to look at it. Now in C, let's say I write this code: A7 equals to H plus A10. Okay, now how will this translate into your Mips code? So let's look at this first instruction here. So in this first instruction, okay, so before we go into that, let's look at some of this mapping that's already been done for us. Okay, so in this mapping, okay, you can see the S3 contains the base address. Okay, so let's draw the array here, A. Okay, so this is the array A, and so the base address S3, so S3 is a register. Okay, and it was pointing to the first element here. Okay, so that is what S3 is contains. It contains the base address. That means the first element in array A. The variable H is mapped to S2 register. Okay, and what I want to do is I want to take the data from A10. Okay, that means this is index 0, 1, 2 all the way until 10, 9. Sorry, 10. Okay, so array index 10 is where I want to take this data from. So how do I go to this location? So I must add an offset. Correct? From here, I must add an offset to point to here. So this is the offset. So how much offset? So since we know that one uh, element, okay, in this case, okay, we already told that each array element occupies a word. That means A0 is one word, A1 is one word, A2 is one word. So each element here is one word. Each element here is one word, okay, which is 4 bytes. So since I am accessing array element 10, okay, array element 10, that is actually 40 bytes away, because one element in the array is 4 bytes. Okay, so the 10th element is 40 bytes away. So that is why we use 40 over here. Okay, we are offsetting from the base 40 bytes. So that is equivalent to array index 10. Okay, and I'm going to take that data and I'm going to put this data into T0. Okay, so inside here there is some data and I'm going to take that information and put it inside T0. Okay, then I do the addition with S2, where S2 is the H, so this is S2 register. So S2 already has the information from H, so I'm going to do the addition, okay, and then I'm going to write back into T0. Okay, so I take this plus S2, okay, and then this result right back into T0. Okay, and the last step is I want to take this entire result and put it into A7. So A7 is somewhere here. Okay, so this result, okay, I want to now take it and write it into here. So to write back to memory, I use the store word instruction. Okay, so when I use the store word instruction, I'm taking the data that I want, which is in T0 register. Okay, and I'm going to write it into a particular memory location. And since this is A7, so that is element 7. Okay, so again comes back to the same idea of byte addressing, but accessing a word. So each element is 4 byte. So index 7 is 28 bytes away. Okay, so it's always with reference to the base. So S3 is the base. Okay, S3 is the base. So since S3 is the base, we are always referencing based on that base. Okay, so it is 28 bytes away, okay, starting from S3. So that is why here you put 28. Okay, so you can see that in C we can write it very easily, okay, because we just look at it from the data and the logic. Okay, but when you translate into assembly, it becomes a lot more tedious, because a lot of things we need to look into. Where is it stored in memory, the base address, the indexing, make sure I get the correct data in, and so on. Okay, so that is the thing we must sort of appreciate over here. Now, we do have other type of instructions, okay, where you can specifically use or manipulate bytes. All right, so in this case you can directly manipulate byte, okay, which is load byte and store byte. So I'm just putting it here for you to know that there are such instructions besides the load word and store word. Okay, but you have to be very careful, okay, in using these instructions, because then you are manipulating a particular byte inside the whole word. Okay, so these are some of the things you need to look into. And when you're doing byte sort of access, you can see that these numbers no longer have to be a multiple of 4. Okay, because only when I'm doing load word and store word, it has to be a multiple of 4. If it's byte, I don't need to stick to that restriction. Okay, so in terms of unaligned access, again there are options using what we call pseudo instructions. Okay, so later I will go through the instruction set. Okay, that is actually inside your Luminous. Okay, but I will go through a bit of that just for you to understand that there are some instructions there which we call pseudo instructions. These pseudo instructions are what we call not pure Mips instructions. That means they do not translate to instructions that are directly executed by the processor, but the compiler will translate some of these pseudo instructions into a few other instructions to help us uh, perform these operations. Okay, so it is not a what we call a pure MIPS. That means it does not translate to an instruction that is actually recognized by the processor. But the software side, the compiler actually helps to do some translation for us so that we can uh, perform this operation using some simple code instead of trying to write something very complicated. Okay, so that is the idea. Okay, so let's look at this example here where we have an array. So in this example, we are trying to translate this instruction A3 equals to H plus A1. Okay, A3 equals to H plus A1. And they have already given us some mappings here where H is actually the S2 register. Okay, S2 register. And the base address of this array A is already given to us in the S3 register. Okay, the S3 register. So let's look at how we can do this. So in the first part here, A1, that means the base is already S3, so that is your source here, and the first element. So array indexing, you all know, you always start from array 0, index 0, index 1, and so on. So in this case, index 0 is basically the base, okay, or where the array is starting. The index 1 will be 4 bytes away. Correct? So that is why we say that this is 4. Okay, so this whole thing here is basically array 1. Okay, and I load that into T0 first. Okay, I load that into T0 and then I do an addition between T0 and S2. So this is your A1, add with your H. Alright, and the result currently I put back into T0 again. And finally, T0 is returned to the destination. In this case, which is A3. So since it is 3, this is 3 times 4, which is 12. So this is A index 3. Okay, so that is basically how we can translate some C code into assembly language code for arrays. Okay, so let's look at a very important concept between address versus value. Okay, and one of the important things to understand is registers do not have types. Okay, so when we say there is this register that is holding information for us, this information could be anything. It could be address, it could be data, or it could be just a collection of bits, okay, giving us some information of what is going on. Okay, so the register is not, you do not need to look at the register and think whether is it an integer, is it a float, is it a character. No. Okay, it is just a collection of bits and it can actually represent a lot of different things. Okay, so there is no implicit data type. All right. Of course, when you are writing the program for some application, as a programmer, you know what it is for. Correct. As a programmer, you know what it is for. It is holding some age temperature, something. Okay, access card number, something. Okay, so that 32-bit number in the register, as a programmer, you may be able to relate to it and say, okay, I know what this is for. But in terms of actual execution and so on in the processor, it will be interpreted according to the instruction in which you use it. Okay, so the same 32-bit data that you have can be interpreted in many different ways depending on how we write the instructions that use this information. Okay, and this is a very good way of putting that across. If I look at these two instructions, add and load, in both these instructions, I'm using the register T0. Okay, but that the way in which the T0 is used is very different in both these instructions. Correct? Because in both these instructions, I'm actually doing an add operation. All right, that part we know. But what is very different is in this first instruction, we are taking the data in T0 and we're adding it with T1 and putting it in T2. So we treat T0 and T1 as containing data. Okay, that means it contains our information. Okay, so it's just like saying x equals to y plus z. Okay, so we can say this is T1 and this is your T0 and this is your T2. So we can relate this in terms of a simple arithmetic operation. But in the second instruction, T0 is used as a pointer to a memory location. Okay, it's used as a pointer to a memory location. So in this case, it is equivalent to saying that x is equals to A0. All right, because T0 is pointing to the base address and I'm adding it with an offset. So the addition in this case is still happening, but that addition value I'm not using. Okay, I'm using the addition value to point to a memory location. Okay, so if I go back here, you can see that. Okay, so if I look at this example, you can see that when I added S0 to 12, okay, so S0 had a value of 8,000 and I add to 12, it gave 8,012. I did not take that as a answer to use. I use that information to point to a memory location. So 8012, which is the result of the addition, is not stored anywhere, okay, in any register. Okay, it is not treated as an answer that I want to keep. I'm just using that result temporarily to point to a memory location. So this addition that happens, okay, is just going to point to the memory location that I want. And then I take the data in that memory location, in this case, which is a word, and then move it to the, or in this case, a store word instruction. So I write the data in the register to the memory location. Okay, so but what I want to emphasize is in this context. Okay, so that's why I said that both these instructions are very different, because in the first instruction we are treating T0 and T1 to hold data, and we want the result of that addition to be stored somewhere. We want that answer. In this second example, the roll over instruction, the T0 plus 0 is just to point to a memory address, and then we want the data inside the memory address. Okay, so in both these cases, we have to make sure that prior to this instruction, T0 is loaded with the correct value. Okay, that means before I execute this add instruction, there must be some other earlier instruction that has already loaded T0 with the correct value, okay, that I want to use for the addition. Similarly, for the load word, before I execute the load word instruction, I must have an earlier instruction that loads T0 with the correct memory address that I want to point to, okay, or the base address that I want to point to. Okay, so these are all the important things we must understand and we must do when we are looking at assembly language programming. Again, like what we mentioned just now, consecutive word addresses in a byte addressing system like Mips differs by 4. Okay, so let's look at this example here. So in this example, we are trying to do a swap. Okay, we're trying to do a swap, okay, between a variable, okay, uh, okay, so we are trying to do a swap between the first variable here, okay, and this k over here. Okay, so in this, basically what we are doing, okay, so let's look at the C code over here. So this temp variable is taking the first in value. Okay, so if I look at the V array over here, so this is doing a swap between any two elements which are specified by k and k plus 1. Okay, so if let's say k is 2, okay, so this is index 0 is 1, 2, 3. So what will I do? I will take the v2, which is this, put into temp, okay, then k plus 1, that means 2 plus 1, 3, take and put inside here, and this one come here, correct? That means whatever index I pass in over here, I will do a swap with the next element, okay, with the next element in this array. Okay, so that is what this C statement is doing. Okay, now how do I translate that into MIPS? All right, so before we do that, we need to do the mapping. Okay, so these kind of mappings, okay, when you are writing your own code, you can decide how you want to do mapping. In if a question is given to you, all right, and you're asked to do something like this, in those kind of situations, mappings would have already been provided, like what you see here. That means we would tell you that, okay, this register is mapped to or this variable is mapped to this register, and so on. Okay, so in this case, k is mapped to register 5, this is mapped to register 4 and register 15. Okay, 5, 4 and 15 are actually the same as your actually all your MIPS registers. Your MIPS basically has 32 registers. Okay, the 32 registers can be accessed using the numbers 0 to 31, or by using those specific alphabets that we have been seeing also. Okay, so you have both names and numbers. Either way is fine. All right, so later when we look at the instruction set, we will see how this can actually be used. Okay, so in this example, let's look at this translation here and try to understand what is happening. Okay, so again, what we are trying to show you is just one possible way where this C code can be translated into MIPS instruction. It may not be the way that the actual compiler does it, okay, and it could vary, all right, but as long as you understand that the logic has to be implemented correctly, then it's fine. Now let's look at this here, first instruction here, SLL5 2 put into register 2. Okay, so the shift left logical, okay, what is happening here? You are shifting the data in register 5 to the left by 2. Okay, now what does this first instruction do for us? Whenever you shift left, okay, whenever you shift left by 1, it is equivalent to multiply by 2. Okay, so whenever you shift left by 1, it is equivalent to multiply by 2. Your shift left by 2 is equivalent to multiply by 4. So what I'm technically doing in this first line is I'm taking my k, which is the index that I want to point to, and I'm multiplying it by 4. Okay, because shift left by 2 is multiplied by 4. Okay, so this is k multiplied by 4. And I'm going to put that into register 2. Okay, why you want to do this? Again, comes back to the understanding that we have that the index is referencing words, correct? So since I'm referencing words, I need to make sure that the addresses are in multiples of 4. Okay, because each word is 4 bytes. So this first instruction is going to do that, taking the data in register 5, which is the k or the index, and multiply by 4 and putting into register 2. Okay, so now register 2 is having the offset. Okay, so register 2. Okay, so in this case, okay, we are giving an example that I put a value of 3 into k. So after I do the first step, okay, which is multiply k by 4, I will have a value of 12 inside my register 2. Okay, so that is the the output of the first instruction. Now in the second instruction, what is happening? I'm taking the data in register 4, adding with register 2 and putting back inside register 2. Okay, so if you remember, add, this is your source 1, this is your source 2, and this is your destination. Okay, for the R-type instruction. So in this instruction, what is happening is, what is in register 4? So register 4 is the base address. Okay, so I'm taking 2000, adding with 12, and then I'm putting it back into register 2. So the value of 2012 is now inside register 2. Okay, so if I come back to this example here, that means, okay, my 2000, maybe I draw it separately here. Okay, so in this case, I have index 3 and index 4. Okay, so the first element here, okay, the first element here at index 0 was at address 2000. The element, okay, at index 3 is at address 2012. Okay, now the next instruction, what is it doing? It is taking, okay, this instruction here, it is taking the content of wherever memory location that register 2 is pointing to with an offset of 0 and putting it into register 15. Okay, so where is register 2 pointing to? Register 2 has a value of 2012. That means it's pointing to this memory location here. And I'm going to add a 0 to it, so nothing will change. And I'm going to take this data and I'm going to put it into register 15. Okay, I'm going to put it into register 15. Okay, so that is what the third line there is doing. Next, I'm going to take wherever register 2 is pointing to and add an offset of 4. So what is happening here? Register 2 is pointing to address location 2012. Correct? When I add 4 to it, it's going to point to the next location, which is 2016. So I'm going to point to this memory location here. And I'm going to take this data here and I'm going to put it into register 16. Okay, so I've done two loads already. One from the first address location, that the data I want from, and then from the next address location, which is the data I want to swap with. Okay, and then what am I going to do next? Okay, so these are the first two load word, and then I'm going to do two store words. So the first store words, what does it do? The first store word takes the data in register 16 and puts it into as register 2 plus 0. So register 2 is still holding the content of 2012. So it's still holding this. So it's pointing to 2012. So I'm going to take this data and I'm going to put it inside here, inside the memory location. Okay, and then I'm going to take the data from register 15 and put it into this memory location, which is the S2 plus offset of 4. Okay, so basically what we have done is we know that we want to swap the data between two consecutive memory locations. Okay, so what this code is doing is it is creating a pointer to the first memory location, take the data, store somewhere. Then the next memory location, take the data, store somewhere else. Then from these two memory locations, I'm going to cross over and write back. Okay, so that is what it is happening here. Okay, and I think the important thing for you to understand is how we are making use of the base address and the offset mechanism to point to where we want. All right, again, this is not the standard or exactly how it would be done, but it gives you the idea of how something like this in C can be interpreted and executed in the assembly level. Okay, so you can see that you need to think very systematically, step by step, where to get the data from, how to use my uh, index addressing. Okay, where should my base point to, where should my uh, offset, what kind of offset should I be using, and so on. Okay, so it is not to say that it has to be done exactly this way. You could have chosen to do it in other ways as well, as long as you know that I have to have a base address and I have to point to a particular memory location depending on the offset and the base address. Okay, so those kind of things you have to think through and then write the code according to that. Okay, so right now what we have done is we have covered the sequential execution so far. All right, and this is of course it still takes time to understand. Okay, so don't be too concerned for now if you think that you're still not very sure yet. Okay, because it takes time to understand the thought process of writing this kind of code. We're just like learning a new programming language. Okay, assembly is also a new programming language for I think most of you. So it takes time to understand the syntax, understand the thinking process on how to write this code. Okay, so right now what we're going to do is we're going to be going into this part here, which is on making decisions. All right, so sequential execution is what you've done so far. Making decision is similar to our if statements, go to statements, and so on. Okay, in general programming, go to is highly discouraged in high level languages. Okay, so even though it is supported in C, it is highly discouraged because it can just make your code look very messy. Okay, and then you also don't know what's happening because everywhere also go to here, go to there, and so on. Okay, so it is supported but is highly discouraged. Okay, because it can really make it very messy. But in assembly language, it is actually very necessary. Okay, because you are having to go through line by line, and using go to instructions, you can specify how you will skip certain sections of the code. Okay. So let's look at some of these decision-making instructions. Um, so the first one, we have two main types. One we call conditional, okay, and unconditional. When we say conditional, that means we are going to be doing a branch, okay, based on some condition being fulfilled. Okay, so these are two most common ones, B and E and BEQ. Branch if not equal or branch if equal. Okay, so the branch will be taken if some condition is met. In unconditional cases, you will jump the moment you execute this instruction without checking for anything. Okay, now in this case, one of the things you need to take note of is label. So a label is something that you can add in your assembly language code that indicates that this is the point that I want to jump to or branch to. Okay, it is just a label, it's not an instruction. Okay, so it is just like a marker, okay, somewhere in your code to tell the assembly language, okay, this is where I want to go to when this condition happens and so on. Okay, so let's look at some of these examples, okay, of conditional branch. In this first instruction, I say BEQ R1, R2, L1, okay. That means if the value in register R1 and the value in register R2 are equal, okay, then the branch will be taken. So when I say the branch will be taken means I will jump to this code starting from the label L1. Okay, so the label is basically, so for example, if I have a lot of instructions, add, okay, so I may have a lot of instructions, and along the way, one of those instructions I can put a label L1, for example. Okay, so I can have some other instructions here, and then I say BEQ to L1 means if this condition is satisfied, I will jump to this label here. Okay, that is how a label is defined in the code. Okay, the C equivalent would be something like this. If A equal to B, that means they are both true, then I go to L1. The other flip side to this is the B and E, branch if not equal. So if R1, R2 are not equal, then I go to L1. So again, in terms of C, we say this is a not equal comparison. The unconditional jump is basically saying that I will just go to this new label without checking for anything. Okay, so if I say JL1, okay, that means wherever L1 is, I will just jump there and start executing from there. Okay, there's nothing to check for. Okay, it is equivalent to say BEQ of S0, S0, because if I compare two registers together, again, it will always be equal. So I can still take a branch. Okay, so that is another way of looking at jump instruction. Okay, so let's look at different ways where a particular C statement may be translated into assembly language. Okay, and try to analyze which one would be better. Okay, in this code here, okay, let's look at the C code first. The C code basically says that we want to compare two variables, I equals to j. If it is true, I do the addition. All right. If it is not true, what must I do? I must skip this line and then come to this line here. That means the line of code that is after this if block. Right? So if it is true, I execute the add operation. If it is not true, I carry on with the next line of code after the if block. So that is basically what the C statement is requiring from us. In this example, I say branch if not equal. Okay, so if it is not equal, I go to exit. Okay, so I will come to this line if it is not equal. So this is the line where not equal. Okay, and if it is not equal, basically I have skipped the addition instruction. Okay, and then I carry on from there. Okay, so that is one way of writing or translating this C to assembly. If I were to do the direct translation, that means I say, okay, since the C code is checking for equal, let me do the equal. So branch if equal S3, S4 to L1. So if it is equal, I will come to L1. But if it is not equal, I must not do the addition. All right. So that is where I say I jump to exit. Okay, so you can see that both of these code are actually doing the same thing, but the one on the right is actually more efficient because it's only 2 lines of code. Okay, whereas the one on the left is 3 lines of code. Okay, so in terms of efficiency, the one on the right is better. Okay, and one of the common techniques you can use is inverting the condition. Okay, so when you say inverting the condition, we look at what is required at the C and we try to invert it. So since here I'm trying to check for equal, I see if writing the assembly language doing the not equal check would be a better or more efficient translation. Okay, so that is basically one way in which you can see whether the first option or second option would be better. Okay, let's look at this example here. So in this example, we have two conditions now, if else. Previously it was only if, now it's if else. So if the condition is true, that means they are both the same. I do an addition, else I do a subtraction. So I'm only going to do one of this, all right? Depending on whether this condition is satisfied or not. So let's look at this translation here. Branch if not equal. So if it's not equals, I go to else. So in else, I do the subtraction. Okay, because this part here is the not equal. Okay, the not equal part, so I do the subtraction. Okay, so that is where the branch to else comes in. But if it is equal, then what happens? If it is equal, I will not take the branch. Okay, if it is equal, I will not take that branch. So I will come here and I will do the addition operation. Okay, but after I do the addition operation, I have to remember that I cannot do the subtraction also, right? So that is why I need the jump instruction here. This is to make sure that I do not do the else condition. Okay, so if I already do the if condition, I must make sure I skip the else condition and go to the line after the else. So that is why the jump instruction is there. Jump to exit. Okay, so you can see that I need to think the sequence very carefully to make sure that I do not accidentally go and execute the code for the else as well. Okay, so that is the thing you need to look at. So in terms of a flow chart, it is basically going to look something like this. Okay, where if I equal to j, okay, then if it is true, I do the addition, else I do the subtraction. Okay, can you rewrite it with BEQ? Yes, is that something you can try? Okay, so you can implement the same logic if I were to do a BEQ. Okay, so if I say BEQ, then okay, so if for example, okay, let's try this here. If I say BEQ S3 and S for, okay. So if I decide to branch if they are equal, okay, that means that is the, I can maybe call it true. I call the label true. So in the true, what must I do? Okay, so in the equal, I must do the addition. Correct, I must do the addition. So if I do not take the branch, that means they are not equal. So if they're not equal, then I'll do the subtraction, and then I must remember to jump to exit over here. So the exit will come here. Okay, so in situation like this, whether I choose the BEQ option or the BNE option, both of the code looks the same. I mean, in terms of the number of the efficiency and the number of lines. Okay, so there's no distinct difference between either approach. It's just a matter of which way you prefer to think. Okay, you want to do a direct translation or you want to think in the reverse logic of the check. Okay, so I think we can go for a break now. Okay, so now it's about 8 o'clock. Okay, so we can take about a 20 minutes break, okay, for you to go and have a quick dinner or something. All right, and so about 8:15, 8:20, I will meet you back here. Okay, and then I will brief you also a bit on some of the material that I've uploaded. Okay, that can help you with starting to write your own assembly language code and do some testing. Okay, so you can go for a break and I'll see you back here about 8:20. Okay. Okay, welcome back after the break. So let me share with you an important document that you will need for this Mips programming. So in your Luminous folder, lecture folder, there is one document here called Mips Instruction Set. Okay, so that uh, document, if you download it, it basically gives you it's basically a reference sheet, okay, for all the instructions that you can actually use for your processor. And of course, it has a lot of more complex instructions that deals with floating point, arithmetic, and so on, which we will not cover. We are only going to be covering the very core fundamental instructions, okay, for our module here. So most of the instructions are here. This instruction format that you see over here on the left uh, is something that we will look into in more detail, okay, once we're looking at the data part and control. And at the same time, if you look at this table on the right, register name and number, this is what I mentioned just now, where the full 32 registers, you can use the names to reference them in the code, or you can also use the numbers. So either way, it will still work. Okay, so if you say register 4, for example, the register 4 is actually register A0. Register 5 is A1 and so on. Okay, so using the names or numbers both ways works. Okay. In terms of the instructions, okay, so for the exam and assessment all, usually if the reference sheet is required, it will be provided in the exam paper itself. Okay, so you will not be required to bring it or print it out or anything. Whatever is needed, it will be provided. Okay. In terms of another important information here for the instructions, you can also see that on this right hand column, there is this thing called, or in the middle is opcode and function. This basically is the way in which the processor is able to differentiate all these instructions. Okay, so like just now what I mentioned, every instruction is 32-bit, but some bits are already reserved, okay, for certain reasons, and one of it is to actually tell the processor what is this instruction all about. Okay, so some bits are already reserved for this purpose, and this information on how the instruction is decoded by the hardware and is able to tell the processor what to do. It's very interesting, and we will actually cover that later on when we're looking at data path and control. Okay, but for now, you can look at this reference sheet as a good sort of a summarized view of the different instructions that you have. Okay, and you can use. Okay, so let me get back to our slides over here. Okay, so we last stopped at this if uh, this slides here, where we look at the if else statement. Okay, so let's look at this question here. So in this question, we are given, so we're looking at it from the other direction, where we are given a assembly language code and we are asked to find the equivalent high level statement, that means in C. All right, so if you look at this, what is happening is I'm trying to check whether S1 and S2 are equal. If they're equal, exit. Correct? Equal, exit. That means I don't do anything. But if they are not equal, then I add 0 with 0 and put into S0. So what does this do? This basically clears S0, correct? Because adding 0 with 0 gives me 0. Okay, and that answer 0, I put it back into S0. So this is equivalent to saying that S0 equals to 0. But I execute this statement if S1 and S2 are not equal, correct? Because if they're equal, I would have exited. I would not execute this line. Okay, so if S1 and S2 are not equal, then I do this. Okay, so of course, in terms of looking at it from the mapping here, you can say that if S1 not equals to S2, then I will assign S0 with a value of 0. Okay, so that is in terms of the register sort of equivalent in C. But since we are given the mapping here for I, J, and F variables, so the final answer is actually here. I not equal to J, which is S1 not equals to S2, then F equals to 0, and this F is S0. Okay, so that is the if statement. Now let's go on to loops. Okay, in loops, basically all you need to remember is that any loop that we want, okay, in C can be written in assembly with conditional branches and jumps. Okay, so the conditional branches that we saw just now and appropriate jump instructions can help us to implement any type of loop in C, from C to assembly. Now in this, let's look at this simple example. So in this simple while loop, we are told that while j equal to k, I increment I. Okay. Now when you look at this instruction in C, of course this is a valid instruction. You must think of rewriting this with in the same C syntax, but using labels and go to instructions. Okay, so if you look at this sort of translation here, it is still in C, okay, but now with labels and go to. So what you have is if j not equals to k, then I go to exit. If not, I increment I and go to loop. Okay, so that is the two things to here. Okay, and that translates to what we see over here. Okay, so now that we can rewrite the loop in terms of go to statements and labels, then translating this to assembly is actually very easy. Okay, because now that I have labels, okay, and I have instructions that say go to, the idea of go to is that I can replace this go to and the associated if with branch instructions. Those go to that doesn't have any check before that, then it is considered a jump instruction. Okay, so this is equivalent to some branch, correct? Because if some condition is true or not true, I will go to some label. Okay, this here is an unconditional, correct? Because I'm not checking for anything, I'm always going back to the loop. So that tells you that this is some branch and this is a jump. Okay, so that is how you can translate, and you can see that here I can say that if S4 not equals to S5, then I go to exit. Okay, if not, I do the addition and then I jump to loop. Just give me a minute now. Okay, so as you can see over here, the first step is always translating the C code into another representation of C with the labels and the code to, and that from that to assembly is a lot easier to see the relationships. Okay, and write your assembly language code. Okay, so let's look at this example here. So in this case, you have a for loop. Okay, and with two variables I and A, then we are going to implement this in Mips. So let's see how we can do this. So the first step is we want to initialize I to 0, which is this line over here. Okay, and then we put the end or exit value to compare with into another register. Okay, S1. So S1 is equals to 10. Okay, so add 0 with 10 is 10, correct? So that puts you back into the S1 register. And then what am I going to do? I'm going to check for the exit condition before I proceed with the loop. So the exit condition is as long as I is less than 10. Okay, so the moment I becomes equal to 10, I must exit. Correct, because I know that in the loop I'm incrementing. Correct, so the moment the I hits 10, I will exit and not execute the body of the loop. So that is basically what I'm doing here. If S0 is equals to S1, that means if I equals to 10, I'm checking for this. Okay, if this condition is satisfied, I will go to the exit label. That means I will not execute the body of the loop. But if this condition is not satisfied, then I know that I is still less than 10. If I is still less than 10, there are two things I must do. One is this, the other is this. Okay, so the first thing is I can add A with 5, so S2 is A, put it back inside S2, and I increment I is S0. So increment I by 1, put it back inside I. And then the unconditional jump, which is J to loop. Okay, so in this case, we are checking for the condition to repeat at the start of the loop. Okay, and the moment the condition is no longer satisfied, I will jump to exit, which is after the loop. Okay, so we have looked at two main inequality branches, equal and not equal. Okay, but how about less than? Okay, so technically there is no real branch if less than instruction in Mips. Okay, but you can actually use what you call set if less than. So there is a SLT instruction. So there is no BLT instruction, but there is what we call a SLT instruction. So this SLT instruction, okay, this SLT instruction, what does it do? It sets on less than. Okay, that means if S1 is less than S2, okay, S1, okay, if S1 is lesser than S2, then T0 will be 1. Okay, if not, T0 will be 0. So how do I make use of this? Okay, so if I want to do a branch if less than, okay, if I want to execute this instruction, branch if less than S1, S2, L. So that means if S1 is lesser than S2, then I do a branch to L. Okay, so this is the logic I want to implement. Now, how can I do this using the SLT and branch combined together? So that is basically, so let's look at what is shown here. So in this first instruction, SLT T0 S1 S2. So what is SLT again? SLT will set, okay, if S1 is less than S2. So if S1 is less than S2, okay, if this is true, then T0 will become 1, correct? If S1 less than S2, okay? If S1 is less than S2, then T0 will be equals to 1. Then over here, what do I do? Okay, so if I look back at my original instruction, I need to branch if less than, correct? So since if T0 is 1, then S1 is less than S2, then I need to take the branch. Okay, I need to take the branch. And if you look at this, again, we are doing it in a reverse way. Instead of branch if equal of T0 to 1, we are saying branch if not equal T0 to 0 to L. Okay. Now, why do we want to do this? Why can't we just say branch is equal T0 to 1? I mean, it is a more straightforward interpretation, correct? Because T0 is 1 when S1 is less than S2. Okay, and if T0 is equals to 1, then I want to take the branch. Okay, but we're not comparing T0 to 1, we're comparing that T0 is not 0. Okay, and the reason is again simply because we have a 0 register, we don't have a 1 register. Right, the 0 register has a value of 0 inside. If I want to compare, if my intention is to compare, okay, if I wanted to compare BEQ T0 with a value of 1 and then branch to L, I can't compare with immediate values. Okay, all your branch instructions, okay, your comparison has to be between one register and another register, which means that this one has to be loaded into another register first. Then I can compare. Correct? So it is an additional step for me. Okay, so that is the basic reason. If you want to compare with a value that is non-zero, then you need to load that value into a register first. So that is one additional instruction for you to execute. Whereas if I compare in this reverse logic and I say branch is not equal T0 with 0 to L, then it is directly you can solve it already, correct, without having to have additional instructions. So that is the reasoning behind this. Okay, there are what we call pseudo instructions, okay, in Mips, which you can use. And basically what the pseudo instruction does is in your code, you will still write it as BLT, but when you compile, it will translate into these two instructions. Okay, so the whole idea of pseudo instruction is to make life a bit easier for the programmer, okay, to implement some of these common operations using the provided assembly instructions, okay, but they will still be translated into two or more instructions at the actual processor level. Okay, so let me show you that. Okay, so if you open up your data instruction set, okay, if you open an instruction set, you actually can see your pseudo instructions here. Okay, pseudo instruction set in the first page itself. Okay, where you have branch if less than, branch if greater than, less than equal, greater than or equal, load immediate, and move. Okay, so these are the pseudo instructions that you have, which are translated into a few other instructions. Okay, so this again to help you with the coding without having to think too much about these steps. Okay, so let's look at this processing of array elements in a loop. Okay, so in this case, when you're talking about, I mean, in C itself, we know that arrays and loops always go hand in hand, correct? Because an array is a collection of a sequence of elements arranged side by side, and the easiest way to index all these elements is to have a loop. All right, so they have always been going hand in hand. So in assembly is also the same thing. All right, the only thing is right now you have to remember that your indexing, when you increment by 1 to the next element, is actually equivalent to increment by 4, okay, to the next word in the array. Okay, so that is the important thing you must understand. Okay, so let's look at this question here. Count the number of zeros in an array A. Okay, so A is a word array with 40 elements, and we want to find how many zeros are there in this array. So in terms of C, of course, it's very easy. Okay, you declare a variable to keep the result, and you go through the entire loop. As long as the compare value is 0, you result plus plus. Okay, so in terms of C, for us, it's very easy, it's straightforward. But what happens when you want to translate this into assembly? Okay, we need to be very careful to ensure that we perform this comparison correctly, and at the same time the this I here, you have to remember that in C we say I plus 1, I plus plus, okay, because the next index automatically points to the next word. Okay, but in assembly it's not the case. Okay, you need to make sure you go by multiples of 4. So that is where the more in-depth thinking is required. So let's look at this example and try to understand what is happening. Okay, so in this example, first thing we are doing is we have already been given a mapping where the address of array A is T0. Okay, that means in your array A, okay, the address of the first element here is pointed to by T0. So T0 is pointing here. Okay, and your T8 is your result. Okay, and your T1 is your count of a loop, the I. And I am going to use another register T2 to store my endpoint. Okay, because this is an array of 40 elements. Okay, what array of 40 elements? So the moment my T2 value hits 40. Okay, so T1 is your I. So the moment T1 equals to T2. So in this first line here, branch if greater than or equal. So if T1 and T2 are the same, that means I already hit the endpoint. Okay, because I should not be the same. Correct? I can go from 0 to 39 in terms of the indexing. So the moment I hit 40, I must exit the loop. Okay, so that is why the first line is there. Branch is greater than or equal T1, T2 to N. Next, your index. So in actual C, you say 0, 1, 2, 3, and so on. Okay, but in terms of uh, assembly language, we know that everything has to be multiplied by 4 for the assembly language equivalent. So that is where the shift left logical by 2 comes in. So that is I multiplied by 4. Okay, so the index multiplied by 4 and I store it into T3. Okay, so in the assembly language programming, you can see that we can use these registers to help us. So we have the A registers, we have T registers, we have S registers, and so on. So these registers, as long as the question never say that you cannot use any of the registers, I mean, some are reserved, which we will see along the way, but most of the common registers, T registers, S registers, and so on, these are what we call the scratch pad registers. That means you can use them, okay, to help you along the way while you are implementing your code. So to store variables, to hold information, to hold account, and so on. So in this case, I shift left T1 by 2, that means it is multiplied by 4, and I store it into T3 register. So T3 register is now going to hold the index, which is now already multiplied by 4. That means based on the actual word address, okay, considering the bytes inside each word. After that, I take T0 add with T3. Okay, so what is T0 add with T3? So T3, what is T3? T3 is going to point to a value. So let's say I'm looking at element 1. Okay, 1 times 4 is 4. And T0, okay, T0 is pointing to the base of the array. So when T0 add with T3, what will happen? It will point to the next element here. Okay, so T0 add with T3 is basically saying that I take the base address, add with the offset. And this offset is based on the I value, the count value. Correct? If I is 1, the offset is 4. If I is 2, the offset is 8, and so on. Okay, but I add it together, so I know the address of where I should point to. Okay, so that address of where I should point to is stored inside T4. Okay, so T0, so what is happening is T0 add with T3 and put inside T4. And T4 is now pointing here. Okay, it's now pointing here. And then I do a load word. I do a load word of wherever T4 is pointing to. Okay, with offset 0, that means there's no offset, and put into T5. That means I take this data, okay, and I put it into T5. Okay, and then so you can see that until this point in the code, all we are doing is trying to get all the indexing, the addressing, everything correct, and get the correct data from the memory to into my register. Okay, so until then, that is all that we've been trying to do. Okay, now only we are actually looking into the logic that we want to implement. Okay, the logic, that means we want to check whether it is 0 and whether it's 0 or not, then we increment the variable. So this is how assembly is. There's a lot of work prior to the logic. Okay, there's a lot of work because you need to make sure your arrays, your indexing, everything is correct. You're pointing to the correct location in memory. You get the data into the processor, then only you can start the processing. Okay, so until now, that's what we'll be doing. Now, from this line onwards is the actual logic. So what we're trying to do, we're trying to take this data, which is now inside T5, and we are trying to compare it with 0. So if it is not equal to 0, okay, so what is the logic you want? As long as it's equal to 0, we increment. Correct? If it's equal to 0, then we increment. So in this case, if it's not equal to 0, that means I do not need to increment. Correct? So that's where I go to skip. Okay, because if it's not equal to 0, I do not need to increment the result variable. So I can go over to skip. Okay, BGE is branch if greater than or equal. Okay, so right now we BNE is branch if not equal. So if not equal means T5 not equal to 0, so I do not need to increment, so I go to skip. Okay, so when I go to skip, okay, what all I do is I increment my index T1 by 1. Okay, T1 is your I variable. Okay, so if you go back here, that is this. Okay, so if the result, if the I, the value in that element is 0, or that element in the array is 0, then I increment my result. If not, I just increment my index. So in this case, if it's not equal to 0, I skip. But it's equal to 0, then I need to do this. So this is the part where I actually increment my result, which is this. Okay, so I add immediate T8, T8, 1. So T8 plus 1 put back into T8. Okay, and then I increment my I, which is this I plus plus. And then I jump back to loop. So this jump back to loop is always happening, it's unconditional. Why? Because the check for whether I need to the check for whether I need to have another iteration of the loop is done in the beginning. Okay, it's done in the beginning, so I do not need to worry about it at the end. I just go back to the loop beginning and then I check. So in this case, I check whether T1 and T2 are still the same. I check whether T1 is greater than or equal to T2. If that is the case, then I would end the iteration, okay, and exit the loop. Okay, so you can see there's quite a lot of steps involved, okay, to make sure that all the initial initialization is done correctly, the pointers are assigned correctly, the offset is calculated, okay, and then I access the data. Okay, that means I move that data from the memory into my register. After that, then I can start the actual logic and then decide what to do, and then I go back and do the next iteration of the loop. Okay, so that is this version 1. Now let's look at this version 2 of the code and just have a comparison between these two and see what is better. Now in this second iteration, what we are doing is we are saying that we are okay. So this at I T80. Okay, so give me a minute now. Okay, so for this you need to what we are doing is we are first setting T8 to 0. Okay, so T8 is your result, T1 is 0. Okay, and what we are doing is we are adding the address, okay, of A into, or you're initializing the address of A to T0, okay, adding it to 0 and putting into T1. Okay, so what is actually happening here? Okay, we are now saying that the address of A, which is the starting point of this array, this address, we are taking that address and putting it into T1. So T1 is now going to point to this address here. All right. And T2, okay, is actually having the value of T0 plus 160. Okay, why 160? Because each element is 4 bytes and you have a total of 40 elements. Okay, so it's 40 times 4, which is 160. So right at the end, okay, of my array is where it is right after my array finishes. Okay, so that is the 160th index. So that is your T2 pointing here. Okay, right after my array. Now, what is happening here? So instead of now looking at it in terms of 0, 1, 2, 3, we are now going to look at it in terms of directly incrementing in multiples of 4. Okay, so let's see what's happening. So T1, T2. Okay, so in this first instance, we are again checking whether T1 and T2 are the same. Okay, but in this case, T1 and T2 are the same means what are we actually comparing? We are comparing the actual address because at the start of the loop, T1 is holding the address of the first element in the array and T2 is holding the address right after the array is completed. If I go back to the earlier one, when I did this comparison here, T1 and T2, what am I comparing? I'm only comparing the I value, the index value. Okay, so in this example, we are comparing the index, okay, the I. But in this version 2, what we are comparing, okay, what T1 and T2 is holding is the actual address of where the data is stored. Okay, and what is the next step? Okay, so of course, if it's already equal, then we already finished the loop, so we end. But if it's not equal, then what do I do? I must take this data and load it to a internal register. So that is this line over here. So load from wherever T1 is pointing to with offset of 0, put it into T3. So I take this data, put it into my T3 register. Okay, so the data is going into my T3 register, and then I directly check whether it is equal or not equal to 0. So if it's not equal to 0, then I don't increment my result. So I go to skip. But it's equal to 0, I increment my result. So that's my result plus plus. Okay, so whatever the case, I need to point to the next element in my array. So since I'm already pointing or holding the address of the element in T1, I directly add it by 4. Okay, so I move to the next item directly and then I jump to loop. Okay, so why is this better? Because you can see that I now do not need to go and do a multiplication. Okay, and I am directly pointing to the memory or my register is directly holding the address of where my data is. Okay, so I don't need to do any other manipulation in terms of changing the offset. Okay, so that is how this code is now a lot more efficient, okay, compared to the earlier code. Okay, so this idea is technically using the concept of pointers. So once I execute the result plus plus, I will still execute the next line, and then I will jump to the loop, okay, the beginning of the next iteration. Okay, and then again I will compare and then decide whether to repeat or not to repeat the loop. Okay, so this is effectively using the pointers, okay, to produce or pointers to directly point to the exact memory location we want. Okay, so this is a second way of doing it. And by doing this way, you don't need to worry about every time recalculating the correct offset based on the index. Okay, because we are every time incrementing by 4. Okay, so that is basically the summary of what you have done so far. Okay, so in terms of arithmetic registers, okay, handling large constants and so on. All right, things that we are not covering here are things like support for procedures. Okay, so in C, normally we have a lot of functions. All right. So when you call a function, what happens? At the assembly language level, there are a lot of things that happen. Okay. When you want to pass variable to a function, where do you store these variables? How does this happen in terms of assembly language code? Okay, so these are things we did not look into, stacks, heaps, and so on, and interrupts and exceptions. So there's a lot more, of course, stuff that you can go into, okay, when you talk about assembly language, but we did not go into all of that. But I think what we have covered so far is more than enough to give you all a good understanding of how assembly language actually is and how it works. Okay, so let me show you one more thing here. So in your Luminous, okay, if you look under labs, I just uploaded this a while back. There is this folder here called Qt Spim. Okay, I would like you all to install this in your system. Okay, so basically Qt Spim is a software that helps you to actually write simple assembly language code in Mips and actually run it and see for yourself. Okay, so you can actually now have hands-on experience, all right, in how you can use Qt Spim. Okay, I have a separate video on how to get started and how to use this, which I will share the link with you all through the announcement. Okay, and that will give you a good way of actually testing your code and to see how it works. Okay, so that is one thing you can do. And another thing is your first assignment. Okay, so there are two assignments. All right, one is assigned, so there's two assignments and one sort of term paper. Okay, the two assignments are split across first half and second half. So the first half, since you're focusing on the Mips, you'll be on the Mips programming language based assignment, and then the assignment two will be on the OS portion. Okay, so the term paper will also be very much linked with assembly language programming, okay, since it covers the first half. Okay, so the assignment one, I will release it this week. Okay, it is basically just a recap and a review of the assembly language programming knowledge that we have covered. As long as you understand the basic concepts of what we have been doing, I think you should not have any problem doing the assignment. Okay, I will also be, I think I just uploaded the tutorial 2 as well. So for tutorial 2, let me just quickly go through the questions. Okay, so for tutorial 2 is just a bit more on the C programming. Okay, just to recap some of the concepts that we have studied. Okay, and at the same time, the last two questions, first two was on C, second two is on Mips. Okay, so we are going to look at how some C code translates to Mips. At the same time, we're going to step through or analyze this code step by step to see how this manipulates the memory content. Okay, so these are the 4 questions for tutorial 2. Okay, so next week, okay, when we meet, we will go through tutorial 2 first. Okay, I'll go to tutorial 2 first just to make sure that everything is good in terms of C programming and Mips. Okay, and then after that, we will go on to the next chapter. Okay, So I know I instead I'll put in some additional questions for the binary and number systems and so on. I will apologize for the delay. Okay, I will upload it by this week. Okay, so you can have some additional practice on some of those number conversion things that we saw. All right, so I think for today we have covered quite a bit. Okay, in terms of the assembly language. All right. Is there any other question that anybody wants? Can you go to if statement again? Okay. Mm. The zip file can't be downloaded. Okay, let me check. Let me check and see whether everything's okay. If in any case there's any issue with what I've uploaded here, you can still just go and search for Qt and download directly from the web as well. Okay, but I will try to check if there's any issue with the zip file here. Okay, if statement. Okay, so the if statement basically there are two main checks in Mips. One is BEQ and BNE. Okay, branch equal or branch if not equal. In the translation, okay, you can always choose to implement the assembly either directly based on the C logic, or you can also think of it from a reverse perspective. Okay, so in this C statement, if I equal to J, F equals to G plus H. Okay, so if I were to think of it in the direct translation, so if I and J are equal, then I uh, do something here. Okay, so I and J equal means in this case, I and J are mapped to S3, S4. So I say branch is equal S3, S4 to a label, this L1, and this L1 is where I will do this addition operation here. Okay, so if I and J are equal, I will take the branch and I will do this addition. But if they are not equal, what happened? I will automatically go to the next line. Okay, so you remember it means everything is sequential. If there is no branch, if there's no jump, you will just execute line after line. Okay, so if I do not branch to L1, I will go to the next line. So in the next line, okay, if I don't put this J exit, what happened? Then the next line would also be the add operation. Correct. So, but I cannot do the add operation if the check is false. Correct. Only if the check is true, I is the same as J, then only I do the add operation. So in order to avoid the add operation, I have an additional jump that brings me to the line just after the add operation. Okay, so that is how you can implement the the if statement directly. You can directly translate from C to assembly. Okay, but of course, this incurs an additional jump statement. Okay, to avoid that, you can improve this translation by thinking in the reverse manner. So in the reverse manner, what we are saying is we check for branch if not equal, S3, S4. So if S3 and S4 are not equal, okay, so if they are not equal means I will come to the line here, correct? The one that is straight after the addition. Okay, so that is what is happening here. This is the line that is just after the addition. Okay, so I will execute this line only if S3 equal to S4. Correct, I will only execute the addition if S3 is equals to S4. Okay, and that is exactly the same logic that is shown here in the C. All right, and this second implementation here is more efficient because it is able to avoid that additional jump instruction there. Okay, so that is how the if statement is. If else is also very similar. You are still checking for some condition here, okay, and whether you choose BEQ or BNE is the same. So in this case, BNE, branch if not equal. So in this case, you have to remember that this is the equal and this is the not equal. So if it is equal, I do addition, not equal, I do the subtraction. So in this translation, BNE means not equal. So in the not equal case, I jump to else is where I do the subtraction. Okay, and then I carry on. But if it's equal, I must do the addition. That means I don't take the jump. But again, like what I mentioned, everything is sequential. So after I do the addition, I do not want to do the subtraction also. Correct? I want to avoid the subtraction. So that is why I need to put an additional jump statement here that will bring me to the line after the subtraction. Okay, so that is the way in which you translate if or if else to BEQ and BNE sort of statements. Okay, so any other questions? Okay, so for the zip file, let me check. Okay, but in any case, if uh, I think if you search for Qt spin, you should be able. Okay, you should be able to get it. It's a freeware. Okay, spin is here. Yeah, so Qt spin is still available for download directly as well from SourceForge. Okay, so you can download directly from here as well. Okay. Yeah, so I think I just put this link. I can send you all the link as well in the chat and in the announcement. Okay, so it's a very old software, so don't worry, it's not like it has been updated regularly or anything. So it's a very old software developed to help us get an idea of how to of writing assembly language on a simulated environment here. Where generally assembly language is run directly on the processor hardware, but in this case, we can run the simulator to have an idea of how it works. Okay, so you can directly download it if the link doesn't work. Okay, let me put it to everyone here. Okay, so that's all I have for today. Thank you very much. Okay, yeah, so I will, as usual, upload the video for your reference, and at the same time, I will upload the assignment one questions as well for you all to start to have a look and see how you all want to approach it. Yes, one more question. Yes. Okay, so you can label them anything you want except same like in C, you cannot have any of the reserved keywords. Okay, so for example, you can't put it. We can't have a label in C like int, correct? Because that is integer. So similarly over here, you cannot have a label that represents an instruction name. Correct? You can't have a label as add or end or something like that. So other than any of the reserved words, you can use any label you like.
Sorry, when is the assignment due? Can I ask?
Okay, the assignment will be due after the recess week.
So in 2 weeks' time? 1 week?
About 3 weeks time lah.
Okay. Thank you. Good night.
Okay. Good night, everyone. Again, any questions, you are free to email me Okay, and I'll answer.